Hello, my name is Haoyang Liu, and this is the final presentation for Purdue University Mechanical Engineering Summer Project Modeling of 3D Nanoprinting. The topic of my work is to identify stress during stitching of 3D parts. Before I begin, I would like to thank Professor Xianfan Xu and Paul Summers for their support through this project. Direct laser writing has gained attention as an advanced method of nanoscale additive manufacturing. However, the size of the print area is limited for direct laser writing, often only on the scale of micrometers. Therefore, to construct larger structures, part stitching becomes necessary. However, inaccurate stitching may cause offset between parts and introduce additional stress. Below is an image of parts that are inaccurately stitched together. It is important to quantitatively analyze the stress in the stitched structure to ensure its structural integrity. For this study, wood pile structures were created as parts in SolidWorks and later assembled together to simulate part stitching. An SEM image of a wood pile structure is shown below. Inaccuracy of stitching was simulated by introducing offset between the parts during assembly. Then boundary conditions were set and finite element analyses were performed on the structures to find the stresses. The material properties were obtained from the paper by Frenzel et al. Shown on the slide here with Young's modulus of 2.6 gigapascals and Poisson's ratio of 0.4. I started with building a simple wood pile structure with square cross-section. The width and height of each rod are both 250 nanometers, and the vertical separation between identical layers is 1 micrometer. The horizontal separation between rods are 707 nanometers, which makes the structure a face-centered cubic structure. After a unit cell was made, several of them were assembled together into a larger structure with 8 layers. For boundary conditions, all bottom surfaces were fixed, and the displacement of 80 nanometers in the downward direction was applied to all top surfaces, which resulted in a 1% strain. The top figure shows the result of a zero offset case with a maximum von Mises stress of 45.2 megapascals. The bottom figure shows the result of the structure with a 200 nanometer offset in the x direction between the middle horizontal layers. The maximum von Mises stress in this case is 46.3 megapascals. Then I moved to building a wood pile structure with elliptic cross-section. Some dimensions of this structure were obtained from the paper by Liu et al. The width of each rod is 330 nanometers, and the height 1.1 micrometer. The horizontal separation between rods is 1.57 micrometers, and the vertical separation is that times square root of 2, which makes this structure also a face-centered cubic structure. Two parts were then assembled together as an assembly, and offsets were applied at the interface to simulate inaccurate stitching. For the stress analysis, the bottom faces of the structure were fixed, and the downward displacement was applied to all top surfaces to result in a 1% strain. The stress values were taken at the interface between the two center rods on the offset plane, which is shown as the red circle in the right figure. From the maximum stress values at these locations for a different amount of offset, we can see that the 250 nanometer offset case has the lowest max stress value, and the 1 micrometer offset case has the highest max stress value. The locations of these values are at either one of the 2 points shown on the center illustration. The low stress value for the 250 nanometer offset is possibly due to it being near the center of the face of the opposite rod, lowering the stress concentration. In summary, the results show that inaccurate part stitching generally introduces higher stress. The maximum stress value generally has a positive correlation with the offset distance, with exceptions that may be due to geometries reducing stress concentration. In the future, work can be done to develop more concrete relationship between offset and stress, and more complex structures such as chiral metamaterial shown on the right can be simulated for part stitching.